This lesson is on the end behavior of polynomial functions. So today we're going to use end behavior so that we can graph polynomial functions without calculators. So today everything you're going to be doing is without the use of a calculator. We are also going to be able to write equations of possible polynomial functions when we are given a graph. So up first, we're going to take a look at the graphs of power functions and then study their end behavior and then see how we can use that when we try to graph polynomial functions. So first up, let's talk about what a power function is. So a power function is any function in the form k times x to the p, where both k and p are constants. So off to the side here, you can see a list of some power functions. These are all where p is an even integer. So we have the function y equals x squared. Now this is something that we know as a quadratic, right? Y equals x squared. But this is also a power function if we let k equal 1 and p equal 2. So we have a few different even integer power functions listed. And then off to the side over here we have odd integer functions, so y equals x cubed, x to the fifth, x to the seventh, etc. So today's lesson is all about the end behavior of functions, and that's how we're going to graph polynomial functions. So let's make sure we define end behavior. So the end behavior of a function, now this says specifically polynomial functions, but this word doesn't even really have to be there. We are looking at specifically polynomial functions. But in general, the end behavior of a function is the behavior of the graph of your function as x approaches positive infinity or negative infinity. So in other words, you're looking at what happens to the outputs of your function as your inputs get really, really large or really, really small. Okay, so this is what happens to your function outputs, which we would call f of x, right? Because those represent the y outputs, as x gets really big. And we're talking huge, right? Because we're trying to approach positive infinity. And it also is what happens to your function. So let me just abbreviate here. So it's what happens to your function values as x gets really small. So as it approaches negative infinity. All right, so let's come back now to those power functions, and we're going to take a look first at the graph of y equals x squared. So we're very familiar with this quadratic, right? We have this U-shaped parabola. We also know the domain and the range here of this function, but let's talk about the end behavior of this function. So remember, end behavior of a function is what happens to the graph of your function as x gets really, really big. In other words, as x approaches positive infinity, or as x approaches negative infinity, or gets really, really small. So let's think about what would happen if we let x be something very, very large. In other words, something like maybe 1 billion. So let's plug in 1 billion into the function. Now, if we plug in positive 1 billion here and we square that, we still end up with a positive value, and this time it's even bigger, right? We're squaring 1 billion, you get something even larger, and that means the end behavior here, as x increases, y increases without bound. Okay, so it increases towards positive infinity as we increase x towards positive infinity. So that you can see from the graph here that your graph is going up towards positive infinity. All right, so now let's take a look at what would happen to the graph of our function as x approaches negative infinity. In other words, as x gets really, really small, what happens to our function outputs? So let's try to input something really small, like negative 1 billion. That's a really, really tiny number. Well, if we square that really tiny number, you actually get a huge output for y, right? You get a huge positive value here, because when you square that negative, it becomes positive. So that's why you can see here, if I just kind of move this point along, even as the x values decrease, okay, the y values continue to increase. So we would say here that the y values increase without bound, even as x approaches negative infinity. So that describes the end behavior of this graph. Now, if we take a look at some of the other power functions here, those even integer power functions like y equals x to the fourth, you can see that the end behavior here is very similar to the graph of y equals x squared. So as x approaches positive infinity, the y outputs approach positive infinity. As x approaches negative infinity, the y outputs approach positive infinity as well. If we look at y equals x to the sixth, you're going to see again that the end behavior is very similar. The graph is just a little skinnier, but the end behavior here is what we're looking at. So all of these power functions with even integers have very similar end behavior. All right, now, as you can see from the graph of this odd integer power function, so we have the graph of y equals x cubed, this definitely does not behave the same way as our even integer power function. So here, the graph of y equals x cubed, as x approaches positive infinity, the y outputs approach positive infinity, but as x approaches negative infinity, the y outputs approach negative infinity as well. So we would say that as x increases, y increases without bound, but as x decreases, y decreases without bound. Now, if you look at the graph of another odd integer power function, y equals x to the fifth, you can see that the graphs are not exactly the same, right? Because they don't overlap at every single point. However, the end behavior is the same. As x approaches positive infinity, your y outputs also approach positive infinity. And as x approaches negative infinity, your y outputs also approach negative infinity. So the end behavior here is the same. If we look at y equals x to the seventh, you're going to see similar end behavior, okay? And that lets you know that whenever you're looking at an odd integer power function, they behave similarly to one another, just as the even integer power functions also behave similarly to one another. All right, so finally, we're ready to start talking about polynomial functions. Now, a polynomial function is any function of this form here, and I know it looks complicated, but basically just means something like this: 3x to the fourth minus 2x squared plus 3x plus 1. Whatever. That's a polynomial function. Now, it has specific properties that we're going to talk about as well. So the graph of a polynomial function has no breaks or cusps. In other words, it's always smooth and continuous. Okay, the graph of a polynomial function should be smooth and continuous. So here I've got a couple examples of functions that are clearly not polynomial functions, because here we've got a break. So I have to lift up my pencil to create that graph here. So this represents a break in the function, where here we have a point in the function that's a cusp. So here's a cusp. It should always be smooth and continuous like that. So we shouldn't have any pointed parts in the graph. Now, we are going to go more in depth with these next two properties listed, but we say that if the degree of a polynomial is n, so in other words here the degree is 4, then the number of turning points in the graph of that polynomial function is at most n minus 1. So in this particular example, there would be 3 turning points at most in the graph of that function. We also say that as x gets very positive or negative, in other words, as x approaches positive infinity or negative infinity, then the polynomial ends up looking like a power function. So that's why we studied power functions so much in the beginning. So to further illustrate that third property, that the graphs of polynomial functions behave like power functions as x gets really big or really small, we're going to take a look at the graph of this power function, y equals x to the fourth, and a polynomial function, y equals x to the fourth minus 3x cubed plus 4x plus 2. So you can see from the graphs of these two functions that we're not dealing with the exact same function, right? The blue graph here has a little bit of a wobble in it when you compare it to that power function x to the fourth. But if you zoom out, you kind of get rid of that wobble a little bit, okay? So your polynomial function starts looking a little bit more similar to x to the fourth. And as we continue to zoom out, now our graphs look even more similar. So we've gotten rid of that little wobble, okay, in the graph of our polynomial function here. And if we zoom out even further, now we can see that the graphs really start to become indistinguishable from one another. So your polynomial function starts behaving like that power function. And as you can see here, the leading term, okay, in your polynomial function, so that leading term would be x to the fourth, it dominates the function. So the graph ends up looking like the power function y equals x to the fourth. Now, we also discussed the fact that a polynomial of degree n will have at most n minus 1 turning points. Okay, so let's talk about what a turning point actually is. Well, yesterday we talked about relative max and mins in the graph of a function, and that's exactly what a turning point represents. So here, if we take a look at n is equal to 3, we have a turning point here, which is representing a relative max, and we have another turning point down here, which is a relative min. It just basically represents the point at which your function goes from increasing to decreasing, okay? And then from decreasing here to increasing. So that's what a turning point is. Now, if you look at each of these pictures, we're showing what the degree is. So here, a degree of 1 means you have a linear function, and clearly there is no turning point. Degree of 2, we have a quadratic function. We have at most 1 turning point. So 2 minus 1 gives me 1 turning point. For a cubic function, n is equal to 3. We have at most 2 turning points, okay? And as you can see, if I just continue to go through with these pictures here for, n is equal to 27, then that would have 26 turning points, at most 26 possible turning points. Now, there's another important tie-in to yesterday's lesson. Remember how we were discussing the zeros of a function? Well, when you look at the degree of a polynomial, so let's say it has a degree of n again, then it has at most n zeros. So if we're looking at a linear function, the degree would be 1, right? It's going to cross the x-axis exactly once, and it has 1 real 0. Now, if you look at a quadratic function, it could have at most 2 real zeros, but it could also have no real zeros. They could both be complex because it might never touch the x-axis, right? Same thing goes for a degree of 3. So a cubic function could have at most 3 different zeros, but it might only have 1 real 0 and 2 complex zeros because it might only cross the x-axis exactly once. So both of these concepts are pretty important when we start graphing polynomial functions without a calculator. So we'll return to those ideas a little bit later on, but now we're going to focus on the end behavior of polynomial functions. All right, so we've discussed already that the end behavior of a polynomial function starts looking like the end behavior of a power function, right? So basically what you're seeing is that the degree of that polynomial function is very important in determining the end behavior, but we also have to look at the leading coefficient of that polynomial function, okay? So both of those together determine the type of end behavior of the graph of your function. So I'm going to go through each of the 4 different graphs depicted below, and we're going to talk about the end behavior of each of these different functions. So I would like you guys to make sure that below here you're writing in this information as I kind of explain it to you. All right, so up first, we're going to take a look at a polynomial function with an even degree and a lead coefficient that is positive. So here we have the graph in green of some polynomial function that fits this general information. Now, as you can see from your graph, as x approaches positive infinity, so as x is increasing, your y outputs also increase as well. Now, you can also see from the graph that if your x values decrease, okay, your y outputs increase, so they go towards positive infinity. So as x approaches negative infinity, your y outputs here approach positive infinity. So this is the information I want you to make sure that you have on your note sheet underneath each picture. It's very important that you understand the end behavior here of each function. So in general, whenever you see a polynomial function with an even degree and a lead coefficient, its behavior looks like this graph here. Okay, so we're going to abbreviate this because in both cases here it's going up towards positive infinity. We're going to say that this is up, up. Now this next diagram in orange shows the graph of a polynomial function that again is even, but this time the lead coefficient is negative. So here we're seeing that the graph has just been reflected over the x-axis. Now this time as x approaches positive infinity, okay, you can see here that the y outputs approach negative infinity. So as x is increasing, y is decreasing. And as x decreases, okay, so as x approaches negative infinity here, your y output approaches negative infinity as well. So in this case, what we'll do is abbreviate this as down, down. So when you have a polynomial function with an even degree and a leading coefficient that is negative, we're going to say that that end behavior here is down, down. Now in the third diagram here in red, we're looking at the graph of an odd degree polynomial function with a lead coefficient that is positive. And as you can see here, as x increases towards positive infinity, your y output also increases towards positive infinity. And as x decreases to negative infinity here, your y output will also decrease to negative infinity. Now, to sort of abbreviate this end behavior in terms of what the graph would end up looking like, we're going to just use the words down, up. Okay, just reading from left to right, your graph is opening downward and then opening upward when you have an odd degree and a positive coefficient. Now in our final diagram here in blue, we see the graph of an odd polynomial function with a lead coefficient that is negative. And as you can see here, it's just this graph in red but flipped over the x-axis, okay? So what we're looking at is end behavior that's a little bit different. So as x approaches positive infinity here, the y output approaches negative infinity. And as x approaches negative infinity, your y output here will approach positive infinity. So if we want to abbreviate kind of what's going on in the picture of this end behavior here, we would say that this is up, down. Okay, just reading left to right again, this is going up, this portion here is going down. All right, now let's come back to our note sheet here so that we can answer this question. Which of the following could be the graph of negative x cubed plus x squared plus 9x plus 9? So in this question here, we have to kind of put together all of that information about turning points, about zeros, and about the end behavior of polynomial functions. So what we'll do is look at the degree of this function. It has a degree of 3, and it also has a negative leading coefficient. Now because of that negative leading coefficient and because of the degree here, I know that this function, when I graph it, it should open up, down. Okay, so from the left, it should open up, and from the right, it should open down. So I can even sketch that. Now, if I look at the options here, clearly the first option is out because that opens down and then up. So this graph could only represent a polynomial function with a lead coefficient that is positive, okay? Now, the next two options could work. Both of them open up, down, right? Up, down. Now, you have to make sure that you're looking at the number of zeros as well as the turning points, though, in the function. So if we look at the number of zeros, this can have at most 3 zeros. So here we have 1 0, that still fits, and here we have 3 zeros. So that one still fits as well. But when we start looking at the turning points of the graph, this function here can have at most 2 turning points. So we take, turning points. We take n minus 1, so that would give me 2, and I can only have at most 2 turning points. Well, this function in the right already has way too many. It's got 4 turning points, so this is not an option. This is the only graph here that could possibly be the graph of that particular polynomial function. All right, we have one last concept to discuss before we start graphing polynomial functions, and that is the concept of multiplicity. So multiplicity is how many times a 0 will occur in a function. So we're going to take a look at this function, f of x equals x minus 2 cubed. Now, just based off of this function here, we know that there is going to be a 0 at x equals 2. Now, we say that that 0 has a multiplicity of 3 because you can see that linear factor here is raised to the 3rd power. So it has a multiplicity of 3. Now, based on the multiplicity of a 0 of the function, you'll be able to tell when you graph the function whether or not the graph should cross the x-axis or simply touch the x-axis at that 0. So for example here, if we're looking at the function, the negative x minus 1 squared here, we have a root or 0 at x equals 1, and it has a multiplicity of 2. So the multiplicity here is 2, which means it's an even multiplicity. Okay, whenever you have an even multiplicity, it's just going to touch the x-axis. In other words, it just bounces, okay, when it gets to that value. So here you can see your graph here bounces off of x minus or x equals 1. It never actually crosses through the x-axis. Now, when you look at something like x plus 2 cubed, here you have a root or a 0 at x equals negative 2, and it has a multiplicity of 3. So here we're looking at an odd multiplicity. In this case, when x is equal to negative 2 here, your graph will cross through the x-axis. So it crosses the x-axis when it's an odd multiplicity, and it just bounces off the x-axis when it's an even multiplicity. All right, now we're finally ready to start graphing polynomial functions. So whenever you graph a polynomial function without a calculator, you're going to want to follow these 3 steps here to the right. And in each of these examples that I'm giving you, I've already got it in factored form. Otherwise, you would have to factor this on your own. But since it's already in factored form, we can just go ahead and jump right into these 3 steps. So the first thing you want to do is always look at end behavior of the function. Now in our very first example here, it's not obvious what the end behavior is because it's already been factored, but let's say we just multiplied all of those terms out together. Well, your highest degree here would have to be x cubed. It's going to be x times x times x. All 3 of these terms here, the product would be x cubed. Now that means that it has a positive coefficient, okay, and it has an odd degree. Remember, those are down up. Okay, so they're going to open something like that, all right? It has at most 2 turning points and so on. Now, we have 3 different roots. Okay, so when it says look at the multiplicity of the roots, we have 3 different roots, but each of these has a multiplicity of 1. Everything is raised to just the 1st power. So when I go to sketch this, okay, I'm just going to draw my graph in like this, and I'm going to sketch a 0 at x equals 0, at x equals 2, and at x equals negative 3. Okay, so these are my 3 zeros, negative 3, 0, and at x equals 2. Now, because I know that it's going down up, because the degree is odd and the positive coefficient here, that means when I graph this, it's going to have to open from downward coming up, so it's going to go through x equals negative 3. Now, I know it's going through because it's an odd multiplicity, so it goes through the x-axis. Then it's going to have to come back down and go through x equals 0. It has to go through this other 0. Then it's going to have to come back up, okay, to finish off. And because, like I said, each of these zeros has an odd degree, it's going through each and going across the x-axis, okay? So it's staying consistent with all the information so far. Now, the last thing we have to do is find the y-intercept, okay? Now, in this case, the y-intercept you can clearly see is going to be 0. But let's say you weren't sure that that's the y-intercept. All you have to do is plug in x equals 0 here. If you plug that into your function, so find f of 0, you have 0 times 0 minus 2 is negative 2, 0 plus 3 is 3. We end up with 0 times negative 6, which is still going to be 0. So you have a y-intercept here of 0. So you're going to always label your y-intercept. In this case, it's already labeled for you. All right, now in example 2, once again, you have a factored polynomial here. So when we look at the end behavior, we need to make sure we just multiply out all those terms. We're really looking at a function with a degree here of 4, because this would give you x to the 4th power. So just be careful, this is x times x times x squared. That's why we get x to the 4th. And it is positive, there's no sign changes here. So we have, again, a positive coefficient. Okay, this time, though, the degree is even. So when we look at that graph here, a positive coefficient degree is even, that means it's going to open up, up. Okay, so my graph, if I just sketch that out, should open up, up. Now there could be some, changes in between. There's going to be maybe some turning points, but that's the general shape will open up, up. Now, when we go to graph this, we know we have 3 distinct zeros. Okay, we have a 0 at x equals 0. We have another 0 at x equals 2. So I'll just sketch in x equals 2 here. And we have another 0 at x equals -3. So it's pretty similar to the last graph. Now this time though, like we said, it's going to open up, up, right? So instead of coming down here with our function, it's got to open on the left-hand side like this. And this time, when I get to x equals -3, I look at the multiplicity here. It's even. That means it's just going to bounce right off. It doesn't cross through the x-axis at x equals -3, okay? Now it's got to go through x equals 0, so it's going to have to come back down and cross through. This time it's an odd multiplicity, so it will cross the x-axis. Then it's going to have to come back up to hit x equals 2, and in that case it's going to go through yet again. So it's staying consistent with the whole up, up. You can see the end behavior here of your function is going to go towards positive infinity and positive infinity, whether x decreases or increases. All right, and finally, we need to find the y-intercept. This is the part that most students will forget to do. In this case, the y-intercept is pretty obvious, yet again, just because it's crossing it obviously at the origin. So our y-intercept is going to be 0, 0. However, if you had to find it, you would just plug in x equals 0 here into your function, and you get a y output of 0. Now, I want to mention that these two functions, if we just take a look at them, they're really, really similar, right? They almost look the exact same. The fact that this was raised to the second power, though, completely changes the graph of your function. So make sure you're paying attention to all of these little details, because you get a completely different function if you don't pay attention to, the multiplicity of your roots. All right, our next example is a little bit different because we have this -1/4 on the outside here. So if we try to multiply out these terms, we end up with -1/4 times x to the 5th. So for the end behavior here, we have an odd degree polynomial and a negative coefficient. So in that case, we know that the graph should open up, down. Okay, so something like that. Now, in this case, when we graph, we just start with our zeros. Let's go ahead and graph those. We have a 0 at x equals -2. Okay, we have another 0 at 3. And those are the only two zeros. Now, because it's opening up, down, that means from here I need to come in from the left with it opening upward. And when I get to x equals -2, I look at this multiplicity. It's an even multiplicity, which means it's just going to bounce off. So at x equals -2, it bounces off the x-axis. It does not cross. And I do need to go ahead and try to get through x equals 3, right? Now, that means I have to come back down, okay, and cross through x equals 3. And this time, it's going to cross the x-axis because I have an odd multiplicity, okay? And it's also going down, right? So it's consistent with that behavior. So this is the graph of this particular function. Now, the last thing I have to do is find the y-intercept. Okay, so find the y-intercept here by plugging in 0 into your function. So f of 0 is going to be -1/4 times 2 squared times -3 cubed. So we get, what is this, 4 times -1/4, that's -1 times -27. So that gives us +27. All right, our y-intercept then is 0, 27. So we go ahead and graph that point. Make sure you're showing it in your sketch as well. So one of the things that you can always do is check to make sure that your y-intercept matches up with what you ended up sketching. Because let's say here, algebraically, we calculate the y-intercept to be -3. That means it's supposed to cross all the way down here, and our graph doesn't do that. So that's a way of checking either you have your end behavior wrong or maybe your y-intercept is wrong. But that's definitely an area where you need to make sure you double check that it's consistent with your graph. All right, now in your last example here, you're supposed to write a possible equation for the given function. Now, in this case, we're not asking you to find a particular equation, it's just a general equation for this function. So there's actually lots of correct answers here, but there are also lots of incorrect answers. So let's go through how you're going to write the possible general equation. So one of the things I like to do first is look at the zeros of the function here. So I have a 0 at x equals -4, -1, and 3. And then I like to write the factors based off of those zeros. So if I have a 0 at -4, then I have a factor x plus 4. And for x equals -1, that factor would be x plus 1. And for x equals 3, the factor would be x minus 3. Now, if you write this as your final answer here, that would be totally incorrect, because if we try to multiply out these terms, we end up with x to the 3rd power. So we're looking at a cubic function here, which does not match the graph, because our graph, the end behavior here is up, up. And for that end behavior, we need a positive coefficient. and then we need an even degree. Okay, so this just won't work if it's to the third power. So we have to go ahead and adjust our equation here. Now, to do that, we'll have to look at the behavior at the roots. So if you look at the function as it bounces off here, that's indicating that the multiplicity, so multiplicity here, is even. So at the factor x plus 4, we have to raise this to an even power. We can make that, x plus 4 squared, or even x plus 4 to the fourth. That's another option. That's why there are many options and correct answers here. But let's stick with the x plus 4 squared. All right, now when we look at x plus 1, we look at where it crosses x equals -1. And here it's clearly crossing through the x-axis. So that means that this is an odd multiplicity. Okay, so we go to x plus 1, and we're going to raise this to, let's do to the third power. Okay, and then finally, when we look at x equals 3 here, it's crossing once again. And let's make this a cubic again. So we have a possible equation, x plus 4 squared times x plus 1 cubed times x minus 3 cubed. Now, just to double check, we do end up with a positive coefficient if we multiply out these terms. And if we add all the powers here, we end up with x to the 8th. So this is definitely staying consistent with the fact that it has to be an even degree polynomial. All right, now if this graph had been kind of flipped over the x-axis so it looks something like that and it was opening down, down, then that means you would need a negative coefficient here. So you would just throw a negative out in front of that equation and that would do it for you. So that could be a possible equation for a graph that would be flipped over the x-axis. Now, next year when you guys get to pre-calc, this answer here, so let me erase because that's not part of our answer here. This answer really wouldn't be sufficient for pre-calc because next year you guys are going to look a little bit more in depth into the graphs of polynomial functions, and you're going to study the behavior of the function near the root, and that will dictate what your possible equation would look like. So for this year though, that's all we're going to do. Okay, we're just going to look at the roots and figure out if they what type of multiplicity occurs at the roots, and then based off of the multiplicity and the end behavior of your function, you can come up with a possible equation. So that is the end of the lesson, guys. Nice job. I will see you guys in class tomorrow.